Video 21, Factors.
Okay, factors. Now, the previous video was all about multiples. Multiples of factors are very, very linked together. What Mrs. Williams showed you last video was 21 is a multiple of 3 and is a multiple of 7. Well, this is very much linked to the way factors work. Factors are kind of the opposite of multiples. So here, we can divide 21 by numbers, we can actually divide it by 3, and we can divide it by 7, and we won't have any remainders. That makes 7 and 3 factors of 21. So I'm just going to put up here, divisible with no remainder. Just as a bit of a reminder for our remainder. Similarly, a factor of 15 could be 1, because I can divide 15 by 1. I can divide it by 3. I can divide it by 5. And I can divide it by 15. So 15 has 4 factors. It has 1, 3, 5 and 15. Now this links to factor pairs. I can think of factor pairs, and basically the factor pairs are the two numbers that will multiply together to make our starting number, in this case 15. So I can multiply 3 and 5 together to make 15, so these are factor pairs, the same way as I can multiply 15 and 1 together. So 15 and 1 are factor pairs for 15, 3 and 5 are also factor pairs for 15. Okay, let's talk about common factors. And looking very similarly to common multiples, we're using a Venn diagram to help us explain this. So here I have a plethora of numbers, and we're looking at factor of 30 and factor of 15. Let's have a look at each of these numbers. 1. Now 1's quite interesting. 1 is a factor for all numbers, because everything can be divided by 1 with no remainder left over. So my 1 is a factor of 30 and a factor of 15, so it's going to have to go in the middle of my Venn diagram. Moving on to 3. 3. Can I times anything by 3 to get me to 30? Or similarly, thinking the other way around, can I divide 30 by 3 and not have a remainder? Well, 30 divided by 3 is 10, there's no remainders, so that is definitely a factor of 30. But it's also same thing for factor of 15. 15 divided by 3 is 5, with no remainders, so 3 must go in the middle. Moving on to 10. Is 10 a factor of 30? Well, 30 divided by 10 is 3, so yes, that works. 15 divided by 10, well actually it's 1.5, so that would have a remainder because it has a decimal number. So that is not a factor of 15, but it is a factor of 30. So I'm going to put it over here. Moving on to 15. 15 is a factor of 30. Yes, 30 divided by 15 is 2, and 15 divided by 15 is 1. So again, 15 needs to go in my middle column. Pardon me. Moving on to number 2. So, 2, is it a factor of 30? Well, yes, because 30 divided by 2 is 15, no remainder, so it is a factor of 30. But 15 divided by 2 is 7.5. So again, I've got that decimal number. I can't, so it's not a factor of 15. So here, 30 divided by 2, I'm going to put it in there. And last but not least, 23. 23, a factor of 30? No, I can't divide 30 by 23. I know that's over half. So if the number's over half, then I can't divide it to get an even number. So I definitely know that that's not a factor of 30. And here, it's even bigger than 15. So that's an impossibility. I can't have a factor that is bigger than my starting number. So there's 2 rules for factors that we can remember. If it's over half, then it's not going to be a factor, and actually if it's bigger than the number we start with, again can't be a factor. So this is going to have to go on the outside of my Venn diagram. Okay, and finally we're going to talk about factor trees. Now factor trees look quite cool, and actually you can draw them in different ways. The idea of a factor tree is it tells you your prime factors. Remember that word, we're going to come on to that a little bit later. But we're starting with 48. Now I'm going to put a square around 48 because I know I can divide 48 by something else and not have any remainders. Now there are a couple of different possibilities. I could divide 48 by 2 and 24, that would be a factor pair. Or I could do 6 and 8, because 6 times 8 is 48, the same as 2 times 24 is 48. I'm going to go with 2 and 24 for this one. So, these are my factor pairs. If you remember what factor pairs are, we can multiply them together to get back to our starting number. So here 2 times 24 is 48. Now 2 is a prime number, and if you remember from the previous video, a prime number means that it's only in the 1 times table and its own times table. Now in a factor tree, we don't go any lower, so as soon as we hit a prime number, that is the stopping of that branch that we are talking about for our tree. So I'm going to put a circle around that so I remember that I don't go any further with that. However, 24 does have factor pairs that is not 1 and 24. I could think of perhaps 2 and 12. So let's have a factor pair 12 and 2. Doesn't matter which way we write them round, it doesn't make any difference. So here again, we know that 2 is a prime number, so I'm going to put a circle around that, but 12 isn't a prime number. We know that there are factor pairs for it. Okay, 12. So we could, we've got lots of different factor ideas we could do here, or factor pairs. I could do 2 and 6, or I could do 3 and 4. I'm going to go with 3 and 4. So here, 3 is another prime number. Again, it's only divisible by 1 in itself, so I'm going to circle that. 4 isn't a prime number. We know it is in the 2 times table, and a factor pair for that is 2 and 2. 2 times 2 being 4. We now know prime numbers that 2 is. Now that is a completed factor tree, and what it does do, it tells us the prime factors of 48. And if I write these out, I've got a 2, a 3, another 2, another 2, and a final 2. So 1, 2, 3, 4, 1, 2, 3, 4, and 1, 3. And a nice little maths magic bit of idea, if I multiply all these together, I should get to 48. So 2 times 3 times 2 times 2 times 2. 2 times 3 is 6, times 2 is 12, 24, 48. And it doesn't matter how we do a factor tree, so long as we follow with our factor pairs rules, it may look completely different, but we will still get the same prime factors, and we will still get the same answers. I will show you over here. Start with 48 again. This time, I'm going to go with 6 and 8. Okay, neither of those are prime numbers, so they're both going to need a branch off. 6, I could do 3 and 2, being a prime number, both being a prime number, and then 8 and 2, let's go with 2 and 4, 2 being a prime number, 4 is not a prime number, but again, the only factor pair I can have for 4, whoops, is 2, 2 and 2. So again, if you look over here, 1, 2, 3, 4 2s and 1 3. So it's going to be written out the same. 3, 2, 2, 2, 2. And as we know about our multiplication knowledge, it doesn't matter which order we multiply these together, we'll still get the same thing. So 3 times 2 is 6, times 2 is 12, times 2 is 24, times 2 is 48. Okay, it's time for you to have a go at home. There are 3 different ways that you could do 36 as a factor tree. I just want you to choose 2 of them. So think about your common factor pairs, your factor pairs for 36, and pause the video, have a go at creating these 2 factor trees. Okay, hopefully you've had a go now and you've worked out the factor pairs for 36, and hopefully you found all of them, but let's go through them. So we could have 1 and 36, we could have had 2 and 18, and we could have had 6 and 6. So their factor pairs, their factor pairs, and their factor pairs. So I'm going to pick 2 of them. Let's go with 2 and 18. So first things first, 2 being a prime number, stops there. 18 is not. Let's go with 2 and 9. 2 being a prime number, 9 not. I could do 3 and 3, that's a factor pair. And again, that would then stop because they're all prime numbers. So 2, 2, 3, 3 are our prime factors. Let's do it again with 6 and 6. neither 6 is a prime number, obviously, but I could split a factor pair for 2 and 3. Again, those are factor pairs and prime numbers. 2, 3, 2, 3, 2, 2, 3, 3. Same amount. Okay, let's just have a quick think about why we didn't pick 1 and 36. Now this goes for any factor tree. If I had have picked 1 and 36, then I'm going to get into an endless repeating pattern. 1 not being a prime number, but I can't actually go anywhere with 1 because, so technically speaking, I would have to claim it as a prime number. We know it's not a prime number, and we know if we multiply anything by 1, it's going to be the same thing. And it creates this endless loop in our factor tree that we will have to keep repeating over and over again, which is why we never use 1 in a factor tree. Okay, let's put our knowledge, our newfound knowledge of factors, onto our number mind map. So I'm going to add it here for ease by multiples. So we have our factors, and if you remember, our factors are something that's divisible, but with no remainder. And then with that, I could find a common factor, which are factors that are factors for two different numbers. I could have had a factor pair. So let's say, for example, we could have had 36 and we said 3 and 12 are factor pairs. And then we could have factor trees which find prime factors. So, what does this link together? Well, multiples and factors, as we know, are very much linked together. The multiples of one factor is going to be the factors of the other multiple. For example, 21 being a multiple of 3 and 7 and 1, actually these are all factors of 21, so it's the other way around. Factor pairs are then linked to multiples as well, and so of which prime numbers and prime factors and factor trees all together as well. Now there's going to be loads, way too many arrows, so I think that is enough arrows from our factors, prime numbers and prime factors. One last link that we need to do, factors link to division. So I'm going to go all the way up here and then cross over into our division.